Good morning, everyone. I want to welcome you to another multivariate statistic class. Of course, in the process of grading and the midterm, one result will be published before the end of the week. Um, and of course, I decided to delay the posting of homework, the current homework, so that will be posted tonight. And of course, the submission deadline will be extended for that. So this week we're gonna finish the material uh, that we started, and we're gonna start another material. Of course, we started inference about single mean vector. Of course, we're gonna be done with that today. And of course, Wednesday and Friday will be committed to situation where we have multiple vectors, and how do we conduct statistical inference in that regard. So the other time we actually stop here on this particular slide 21. We're going to finish with that today, like I said. So let's start. Linear combinations of normal variables. So if I have um random variable, if I have a vector x, which is a set of explanatory variables, and the belief is that that follow multivariate normal distribution, okay, with a vector mean and the covariance matrix. Now, if there exists a constant, okay, a constant vector, okay, that also lies in p-dimensional state, okay, and we can actually define a new variable, which is going to be a linear combination of the variables, the random variables we're talking about, and the constants. And of course, if z is a random variable, okay, we need to be able to investigate what is going to be the mean and the variance, because if x1 up to xp, they follow multivariate normal distribution, we also expect the linear combination of that to also follow normal distribution. Now, if I really want to have a probabilistic computation, okay, based on a linear combination random variable z, then I need to be able to figure out what is the mean, what is the variance. So if a particular random variable follow normal distribution, okay, and if we want to conduct an inference with a particular variable, we need to be able to, have the knowledge of the mean and the variance before a meaningful inference can be conducted. Now, when you take a look at what I have right now, that is the mean and that is the variance. So what you can see, the mean is a combination of the constants and means. Okay, the means, the vector mean of the variables that we're talking about. And of course, if you take a look at the variance of z, you can see A transpose the covariance A. The covariance that we're talking about will be the covariance of the random variable x1 up to xp. So let me tell you this. When we're talking about statistical inference can be divided into two things. I can Classical inference is about like testing. I can decide to test hypothesis about this particular linear combination. I can also construct a confidence interval. So what I'm going to show you today, we got different kinds of confidence interval approach that I'm actually going to showcase. And I'm also going to tell you the reason why we got different kind of confidence interval approach. Now you have the understanding of what the mean is and of what the variance is, so that I can boastfully tell the world that okay, the linear combination, the random variable z follow normal distribution with a mean of mu z and the sigma square z. Okay, so I just wanted to take note of that. Now, moving forward, what I actually show you here is, talking about the population distribution. But if I want to apply on sample data, because apply, we always apply on sample data. If I want to apply it on sample data, okay, I'm actually believe that my xi, okay, ID follow multivariate normal distribution. And of course, the zi is a linear combination, meaning we can have different kind of linear combination. That's how you say zi. Okay, it could be z1, z2, and so on like that up to n. Now, the sample mean and sample variance is needed because actually we are having sample at our disposal. So right now, if you take a look at what I have, the z bar is the mean, is the sample mean. Okay, why this guy is a sample variance? There's something I needed to take a look at, take a look at this guy. That sample covariance is different from population covariance. This is a population covariance. Can you see that? That's a pop that look like a sigma. That's a population covariance. This is a sample covariance. Okay, we use sample covariance, when the attention is on we're working on the sample. And of course, I want to find the sample mean. I need to be able to have how am I going to compute sample mean vector, because the x bar here is sample mean vector. In a sample mean vector, of course, you have several means, and what is the formula you're going to use to figure out the mean, which is this guy here. And of course, you take a look at the sample covariance, take a look at that, okay? That is the sample covariance. Now, the moment I have that, let me tell you this. When I compute, please, I need you to pay attention. When I compute any of that, I'm only going to have a point estimate. I'm only going to have, I'm only going to have a point estimate. I'm only going to have a point estimate. So what I'm trying to say now, okay, this equal this, okay, and this equal that, okay. I'm only going to have a point estimate doing that. A point estimate is when we get a single value result in a point estimation, and a single value could be wrong or right, and that is the reason why we may need an interval estimate. The interval estimate, because this guy is not reliable. The point estimate is not reliable, and that's why we actually want to have an interval estimate where we're going to consider we're going to incorporate margin of error. Okay, the margin of error. Okay, and that which is going to be more precise. Okay, now based on what I have right now, we move into confidence interval. We consider confidence interval because it's working with a point estimate. It could be wrong or right. It could be too high. The value we got could be too high or could be too low because these are estimator. They are estimator. They vary. If I have 1,000 researchers to go into a population, they work on the same thing, they're going to have different values for this. So because it varies, okay, just having a point estimate for it may not be reliable. And that's why we need an interval estimate. Interval estimation is actually required in order for us to to have a measure of precision. Now, because of that, we are considering an interval estimation. Okay. Now, in the considering interval estimation, we want to go by way of a t-test. Okay, the classical t-test approach. You remember my z bar is a prime x bar, and the mu z. What is the difference? Please, I need you to pay attention. One is a sample mean, the other one is a population mean. Okay, the z bar is a sample mean. Okay, so if you take a look at, please pay attention. We're working with a very serious notation. Okay, this is the formula here. That's a sample mean. The mean you got from the sample. But this guy here, that's a population mean. So A prime X bar is different from A prime mu. Does that make sense? And of course, if you take a look at this guy, okay, it's actually the standard deviation, which is the square root of this guy, the square root of the variance. Okay, now we're using a classical T approach to derive the confidence interval. I told you the reason why we need confidence interval. Okay, a point estimate will give us a single value that may be wrong or right, that may be low or high, and that's why we need to generate an interval estimate that we can boastfully say the population vector mean lies with some degree of confidence. Now, I'm actually going to show you what the final derivation is going to be. The final derivation is actually, please pay attention. The final derivation is what we have here. Now, if you take a look at it, you're actually going to see that we have if you take a look at, give me 1 second. This is the sample mean of the linear combination. So what are we doing? The sample mean of the linear combination, everything here is a margin of error. We're subtracting margin of error. And in the margin of error, I'm going to show you the margin of error is a combination. Let me tell you this. The margin of error is a combination of a standard error and the T quantifier. Okay, you remember in univariate statistics, we normally have this, right? Which is going to be this. Can you see that in a univariate statistics? That's what we have. Okay. In a univariate statistics, that's what we have. Of course, in a univariate statistics, this guy is a standard error. Standard error. This guy, okay, T quantifier. Okay. Now the combination of the two, okay, give margin of error. Okay. which is exactly, if you take a look at what I have in a multivariate case, okay, you can see what our standard error is and what the quantifier and the entire thing. So this approach here, we're using the classical T approach, okay, for the simultaneous confidence interval. The simultaneous confidence interval here, we believe that the possible, the plausible range of values for multiple parameter we actually lies in the interval. Now, I needed to pay attention to that. So that is one way to construct a confidence interval. Now, I'm going to tell you what is the limitation of this guy. You know, the limitation of this guy is actually, you know, it has a there's a tendency that the probability of committing type 1 error will be exceeded. I'm going to say that again. So using this approach, because this is going to be done multiple times, there's possibility. The probability of type 1 error will be exceeded. When the probability of type 1 error is exceeded, then the probability, it means the chance of taking incorrect conclusion increases. We don't want that kind of situation where the chance of taking incorrect decision increases. And what we're going to do is there a way we can actually have a robust conclusion, okay, when multiple comparison is actually involved. Can we have a robust conclusion when multiple comparison is involved? When multiple comparison is involved, you're actually going to have so many tests. Okay, the fact that you have more than one test, okay, that will increase the probability of type 1 error. We don't want that to happen, because when the probability of type 1 error is exceeded, of course, it means the chance of incorrect conclusion increases. And what are we going to do? We need to have some adjustment. So this is exactly what I'm trying to say. The confidence interval has a level alpha separately for each confidence interval, okay? And of course, for multiple confidence interval, the family-wide significance level will exceed alpha. Alpha here is a maximum probability of committing type 1 error. So the maximum probability of committing type 1 error will be exceeded. We don't want that, because we got multiple, confidence interval that we want to compute. And what do we need to do? If we want to form a confidence interval for each mean time, we need to consider some approach that will control the family wise error rate. Okay, we need to control the family-wise error rate. We're able to control that. It means we're restricting the type 1 error to a threshold. It's not going to be exceeded anymore. Okay, and one of the approach is to consider simultaneous and uppercase T-square confidence interval. Simultaneous uppercase T squared confidence interval. The one we considered before was a classical T. Classical T. Okay. The one we considered before was a classical, okay, classical T approach. But the one we want to consider right now, okay, is actually simultaneous. Okay, the simultaneous means it's going to operate, it's going to conduct everything at a time. We're not going to have so many tests. It's just going to be once. Okay, so now that idea is actually going to come from T squared. You remember here the other time we did not square T, right? Where we're deriving the classical one. You can see with the we square T, we didn't square T, right? We didn't square T. But right now, we now want to square T, okay? You see that? We're squaring T, and after squaring T, then we're going to derive We want to derive now. Take a look at this now. This is what we've derived. Okay, please pay attention to formula. We play with the formula here. Take a look at what we have right now. We have a new confidence interval based on simultaneous uppercase T squared. Okay, this formula now is different from the one. If you compare this formula with the one that we did before, the only thing that is common, I'm going to show you what is common. Okay, what is common? This guy is there. This guy is still there. But the only thing that changed is the quantifier. Quantifier. When you take a look, I think I'm quickly going to show, I'm quickly going to go back so that you're going to see what I'm talking about. Please pay attention. Okay, pay attention. This course is so easy, very simple to. Now, take a look at this. Compare this guy right now. You can see the only thing different between this formula and the one I want to show you is T. Here, this one has what? A T quantifier, Tn minus 1 alpha over 2 based on a classical T. But if you take a look at the other one now is based on the Ottolin T squared. And of course, the Ottolin T squared has something to do with what you have in the square root. Take a look at that. The VMP, FP, M minus P. That is just the difference between the two. Now, I've presented to you right now the formula that I'm actually showing is, you know, is the simultaneous confidence interval based on Ottolin T squared. Okay, now that is that. And that formula is going to be, we believe that this, the A prime mu, which is the population mean parameter, will lies in the interval with the level of confidence 1 minus alpha. Level of confidence 1 minus alpha. Don't forget, alpha is level of significance, which is the maximum probability of committing type 1 error. 1 minus alpha is a level of confidence. Level of confidence is different from level of significance. Level of significance is a level of statistical error, which is the maximum probability of committing type 1 error. Okay, now you've seen that right now. Okay, making 2. Okay, now if we have that guy now, I think we are ready to go into R. Now we have formula. I told you the other time without formula. Okay, somebody that is programming, that is doing a programming, we may not be able to program anything. Now that we have a formula, now we want to go into programming. Okay, now this is the TCI. Okay, this is it, a confidence interval, the TCI one, if you want to write the coding out. Okay, and of course, I can give you an example on how to construct a simultaneous Ottolin T-square confidence interval that I just show you right now. If you're giving read that I said. Now I got read that I said. This is in R, empty cows. This that I said. It's actually in R. You have the MPG, the DISP, HP, and WT. Okay. Now, of course, you need your hand, you need your P, you need the color means, you need the variance covariance. This is the X bar, and what you're seeing now. Take a look at that. We are at, oh my God. We're not. If you take a look at this, please, I need you to pay attention. I needed to pay attention. Look at the guy. I said something the other time. I mentioned points, estimate. What do I mean by that? If you look at the MPG, I only have a single value. 20.09062. That's a single value. For DISP, I got a single value. Okay. For this, I got a single value. You know what happened? The single value that we have could be wrong or right. Does that make sense? The single value that we have could be wrong or right. Okay. And how are we actually going to have a more reliable estimate is by incorporating the margin of error so that we actually that will enable us to construct the interval estimate. Now, instead of me to just say, oh, the average MPG is 20.09062, then I'm actually instead I'm actually going to say this. It's going to make more sense, describing results in an interval. than presenting a point estimate that could be wrong or right. Imagine you committed resources to your research only to be let down by poor statistical tool at the end of the day. You don't want that to happen. Now, now we are having that simultaneously for all the variables. If I have four variables, I'm actually going to have, four, confidence interval. Is there any question on this? Any question on that? Okay, now that's how that is done. Now, I just show you that. But you know what? The next thing I want to talk about, can we have a way to compare two form of a confidence interval that I've discussed? Don't forget, when I started with a classical T confidence interval where I did not square the T, right? And and I go to the another one where I actually use the idea of Ottolenghi squared. Now, can we have a way now? Okay, can we have a way to compare, the two intervals, to be able to know the one that's appropriate for our data set? That's what I'm doing here. That is what this code is about. Oh my God. Take a look at that. For instance, for each variable, this is going to give me an opportunity. Take a look at that. Now to compare the confidence interval for the Ottolenghi square. The Ottolenghi square is a upper TCI. Then the classical T is the lower TCI. Now you can see the confidence interval. You can compare for each variable. Take a look at that. You can compare for each variable. Okay, I want to award an extra credit. Okay, now I remember extra credit. Um, Immediately you see your result for midterm. For those of you who have earned extra credit in my class, you can send me a message. Of course, I'm going to actually make an announcement through the Canvas that for those who have earned an extra credit, immediately they've seen their midterm result, they need to send me a message on how they want to spend their extra credit. Somebody can say, okay, can you add my extra credit to the midterm one? And somebody can say, okay, you know what, I'm okay with what I got in midterm one. I want to save my extra credit, probably for midterm two or the final. Does that make sense? Okay. Now, take a look at what I have now. Now, I want to award an extra credit now based on what you see. If I want to choose a confidence interval, appropriate confidence interval for this data set, which one do you think I'm going to choose between Ottolenghi CI confidence interval and the classical confidence interval? So which one do you think I'm going to choose? And if you tell me the one to choose, why do I need to choose that? Can somebody answer the question for extra credit? Go ahead. Okay. You said the lowercase TCI because it has a lower interval, which means it has a lower range, right? That's a good one. Send me a message for extra credit. That's correct. So when you take a look at what I actually have right now, okay, what I have right now, if you really want, what make if an interval is wider, if an interval is wider, then it means it has a larger margin of error. And what could be responsible for a larger margin of error is the standard error. When standard error is large, the margin of error is going to be large. Does that make sense? And the one we can actually trust, okay, is the one with a narrower margin of error. Does that make sense? That's a good one. Okay, now I actually want to move right now. Um, you know, this is not the only tool that we have in literature. Okay, we may also want to consider, other more precise, simultaneous confidence interval. When I say more precise, what do I mean by more precise? I'm actually looking for the one that, we got the range is going to be narrower. What's gonna make the range to be narrower? What's gonna make the range to be narrower is when the margin of error is very small. Okay. And because of that, we actually want to consider, there are different kind of den. We have the Bonferroni, okay? We have the Bonferroni, we have a bootstrap simulation-based approach and so on, like that. Some are liberal, some are conservative. But right now, let's first take a look at this. If P, which is, when I say P now, I mean the number of variables. Okay. If P or the number of linear combination, AI up to EQ is small, okay, we may be able to form a better, narrower, simultaneous confidence interval. Okay. And in that regard, I'm going to say, let CK denote some confidence statement. And what is a confidence statement? The probability that all CK, okay, is true, which is going to be 1 minus probability of at least one CK is false. Of course, in statistics, the probability of you know uh uh probability of S equal to or maybe greater than one, greater or equal to one, for instance, if you have this in statistics, the probability of x greater or equal to 1 would be 1 minus probability of x less than 1, which is 1 minus probability of s equal to 0. If s is discrete, okay, 1 minus probability of s equal to 0. So the probability of s greater or equal to this, at least 1 in statistics, at least 1, okay, it's going to be 1 minus probability of, s equal to 0. So we're using that here, okay? At least one CK is false, okay? So when we do that, what is the probability of a CK? The probability of a CK is the alpha K, which is the level, is going to be level of significance used for each confidence interval, okay? Now, but we know the other time that when the number of the of confidence interval that we want to construct increases, the level of significance actually going to be inflated. The level of significance is the maximum probability of committing type 1 error. Now let me tell you what Bonferroni did. Bonferroni actually want to have a way to improve on confidence interval estimate. Okay. Yeah, and the only thing we can do, what he did is, okay, can we have a way to adjust the error rate of the individual test? Individual test is going to use alpha K as a level of significance. Okay. So what Benferroni did, Benferroni actually used this. Okay. He adjusted the alpha K to be the level of significance divided by the number of tests or the numbers of intervals you want to construct. Okay, with that, the level of significance will go down, right? Will be reduced because you are dividing the level of significance alpha by a Q. That Q is positive. So we expect alpha K to be very small. Okay, that was what he did. Then after that, he incorporated, please pay attention. If you take a look at this now, he incorporated that. Instead of us using alpha, we're no longer using alpha. What are we using? We're using alpha K. Can you see alpha K? Okay, alpha K is alpha K is alpha divided by Q. What is Q? The number of confidence interval or the number of significant tests. Okay, and we said here, if we have a prior knowledge about the importance of individual tests, we could adjust each alpha K individually, okay, with what we just did. Okay, and after doing that, that may work, that may not work, depending on data set. Now, if you want to know whether it's work, this is the coding now. Okay, for that Benferroni, and Do you know? Oh my God. Do you know what I've done again? What I've done again and again and again is to compare. Now we have three type of confidence interval. Now we started with the classical confidence interval, the one based on classical T. We move to the Ottolenghi square confidence interval. Now we are at Bonferroni, B-O-N, Bonferroni. So we got three confidence interval that we want to compare for each, variable. Okay, and you can decide on which one that you want to exploit. Okay, now another we have another confidence, another way to, this another one, asymptotic inference. When we talk about asymptotic inference in multivariate means, asymptotic means when sample size increases. That's what we call asymptotic. When I have a large sample size, when I have um a very sufficiently large interval, okay, now suppose we have x1 xp, okay, they are random sample from some distribution. They have a finite mu and a finite covariance. Now what happened to the distribution when sample size goes up? You know what? When sample size increases, that's what I mean. It tends to infinity. What will happen to the distribution? The distribution, we converges to multivariate normal with a mean of 0. The vector mean is going to be 0 with this. And this guy, okay, we follow a chi-square distribution. Take a look at that. That guy follow chi-square distribution. The other guy will follow normal distribution with a mean vector 0. And that is when sample size is large. Okay, at times, if you are working with a sufficiently large sample, can we also have a way to actually, conduct a test, a t-test, or construct a confidence interval? Okay, in that situation, the conventional test will be adjusted. The conventional confidence interval will also be adjusted to reflect the asymptotic that we talk about. Now, if you take a look at this now, this is having a code for, what are we updating here? The conventional t-test, we now updating that we are adding asymptote. Asymptote means large. And how I'm going to show you something now. Uh, you're going to see, okay, now let me come here, take a look at this. You see this result? This is the one without asymptote. You see that? What did I say? Asymptote false. Okay, I want to compare that with the one with an asymptote. True. Okay, is there a change in the p-value? Yes. The p-value in one is 0.85. The p-value in the other one is 0.74. So you can see a change, when you are working with a sufficiently large sample. Of course, you can see it affects the p-value. That's exactly what we're trying to show here in this test. Okay, this is a simulated. We're using a simulated data. Okay, we're simulating from a multivariate normal in R. Okay, 10 by 4, you can see what we have. Okay, so that's an example of what I just talked about. So these are just a code, okay, for a situation where you consider asymptotic situation where you did not. Okay, where actually I just wanted to see that. Now, from the test, can we also reflect asymptotic last sample a confidence interval as well, so that we can have a way to compare with the three different type of confidence interval we've derived today? Don't forget, we've derived the classical T, the Ottolenghi square confidence interval, and the Bufferoni. Okay, can we also have another one? Can we add another one to the list? Okay, the another one that I want to add to the list is the asymptotic one. Okay, and don't forget, okay, we said something here the other time. Okay, this is going to follow chi-squared, right? Okay, now the quantifier is going to change. Okay, now let me just quickly. So if that follow, if we believe that our t-square now will follow a chi-square. Why do I say t-square following a chi-square? Where do I get that from? Please pay attention. Don't forget, I said something here. Here. Can you see this guy? Follow a chi-square? Don't forget, this guy is a t-square. Do you remember? That's a t-square, right? If you check the note, the whole of this. The whole of this guy. Oh, give me 1 second. The whole of this guy. That's a what? That's a t-square. So what happened now? T-square following what? T-square, Ortelin t-square distribution will become a chi-square distribution if sample size is large. That's what we mean. When sample size is large, Ortelin t-square become a chi-square. So now that is if the sample size is large. And that is what we want to incorporate here. Okay. Now we said t-squared for large n, t-square, Ortelin t-square distribution behave like a what? A chi-square. So if I'm seeking a confidence interval now, then I'm going to say the probability of an Ortelin squared less or equal to chi-squared will be much more the confidence level. Now, at the end of the day, I'm going to show you the formula. Oh my God, this is super easy. Look at the formula now. Something still remains the same, except what changes. What do you think that changes? It's just this. Can you see that? It's just that. Every other thing remains the same. Look at that. Okay? The chi-squared, the quantifier side now. It's a chi-squared. Okay? Now, can we have a way now to compare the four? We have four different kind of interval now. Okay? On the same data set. We're back. This is the code. Oh my God. How many are we having now? I'm actually calling that chi. Okay, the fourth one. Do you see now? How many do I have? The TCI. Okay, the Ottolini square confidence interval, the classical confidence interval, the Bonferroni, and the one for the chi-square now is the asymptotic one. Don't forget the t-square, the Ottolini square become a chi-squared when the sample size is large. Now, this is going to give you an opportunity to compare, okay? You know, for instance, for NPG, you can compare the range, okay? The one you're going to settle for at the end of the day, okay, it depends on your data set, okay? You know, Ottolini square confidence interval may be good for this data set and Bonferroni may be good for another data set. So if I were you, if you want to construct a simultaneous confidence interval, whether, you know, what are we constructing, simultaneous confidence interval on? We could construct it on the means, multivariate regression means parameter. We could construct that for eigenvalues or factor loading in dimensionality reduction technique. Okay, we could construct that in a discriminant analysis where we compute the probability of classification. The probability of classification, you're actually going to have a point estimate probability of classification, which is not going to be reliable. You can also incorporate the margin of error, thinking about constructing confidence interval in that regard as well. But let me tell you this. How do I know the one that work? The one that work is the one that have a narrower interval. A narrower interval. And you know what you can do if I want to know? I can do 23.78 minus 16.40. Compare with 22.26 minus 17.92. You know, the one with the smallest range is the better one. The one with is the one with the narrower interval. Okay, you do that across. Okay. Okay, now finally, what do I have? Finally, the prediction region for future observation. This is the final thing today. How do we create what I call a confidence region for prediction? Okay, and for predicting a future observation. For instance, the one we've been doing, we've been having confidence interval for means, but this time around, confidence interval now for prediction. It's like prediction region for future observation. Okay, I still have this guy. I have his mean sample mean vector and sample covariance. Then I'm going to give you the formula. Now, let us assume that this is a new observation. Can you see that? We want to make a prediction. That's a new observation. Okay. Now, and that very new observation, where is it going to come from? It's coming from the population, not from the sample, from the population. Okay. Now, we're going to compute an Ottolini square for the new observation. This is the Ottolini square for the new observation. You can see n over n plus 1. The S star is the new observation. The X bar is the mean sample mean vector. And that follow this distribution. Now, remember that also take note that the covariance of that guy is the same thing as this. Okay. Now, I'm quickly going to show you, now that I've shown you that, okay, we have a code. We got a code in out. Oh, give me 1 second. Okay, now this and the 100%, 1 minus alpha prediction episode is given by day. So we really want to see which the region that we have so many, the future values is going to lie. Now you know what I'm trying to show you here. What I'm trying to show you here is a scatter plot for two different bivariate. Okay, if you take a look at this, okay, HP against that, this is telling me that there's a negative relationship. And if you take a look at 0.99, 0.95, 0.9, their confidence level, okay, 99, the highest confidence level is the one so many of the future values will lie. Does that make sense? That is what it's giving you. But if you look at the relationship between HP and displacement, it's positive. If you look at that. And also here, this also gives us a different possible confidence level. The prediction values is actually going to lie. Okay. So take a look at that. And of course, if you want to have a code, I think I put a code here. It's a code now. Do you see that? That is a code now. What are we going to do next? Now, what we're going to start on Wednesday. We've been having inference about a single vector mean, but this time around, we want to extend to inference about multiple vector means. A single vector mean is more or less like a school. It's like a school is a school make a claim that the average performance of their students in maths, science, and reading is this, and that, because that's a school. That's a single setting. That's why I call a single vector. But right now, what we're going to start on Wednesday, we want to now go beyond just one school. So many schools. Can we have a way to compare the performance in maths in this school with that school? Can we compare the performance in readings across schools? And that will lead us to inference about multiple mean vectors, because multiple schools are involved, or multiple settings are involved. This is very crucial in psychological study, in medical studies, and economy studies, and in most of the studies in general. This is where I'm going to stop today. Like I said before, the end of the week, the midterm one results will be published. Be sure you all stay safe and have a lovely day. Bye for now, everyone.